to describe the work that we have been doing with these two young fellows and with Ehud that is sitting here, trying to cross, to go from ideas that were developed in the community of ultra-cold atoms and take them, or maybe take them back into nuclear physics and see what comes out. So as such, these talks will go between these two languages, the language of atomic physics and the language of nuclear physics. So I apologize for both communities. I try to make this marriage work, but it might be that out of my shortcoming, I will not be explain properties that are on either side in the proper way. So if something is not clear enough, just ask. This is a workshop. So I will try, after some introduction to things that you already know, I will hopefully go to things that you don't know, and then at the end present some experimental results. So few comments about the contact. So this is now known as Tan's relations after Shina's work. So we consider a system of fermions, two species of fermions that interact with a short range interaction with I use this R naught to define the range of the interaction. And the point is that this number, the range of the interaction, should be smaller than any other meaningful dimension in the system. That is the de Broglie wavelength, or the volume of the system, or the density. And under this assumption, you can write some very smart relations between the momentum distribution, the energy, and some other properties, and they are all related to one quantity that is now known as the contact, that is denoted by C. So C is this contact, and it appears, as I was saying, in the tail of the momentum distribution, in the energy relation, in some other relations that really goes and connect this microscopic property to the macroscopic properties of the system.
This assumes only two-body forces?
What? This assumes only two-body forces, yes.
Why
But this is in Shina's derivation, it was assuming. But in principle, the contact can be defined for any system, regardless if you have two-body, three-body, four-body, six-body system. It just connects to what happens when two particles are coming close together. I'll get to that in the moment. And I think that also in the context of atomic physics, there is works by Levinger and Constant where they include also three-body effects into the business, right?
The case of fermions.
Yes, in the case of fermions, yes. Now, after the publication of Shina's work, there were a few experiments that tried to verify these relations, and they indeed found this one of a k to the 4 tail in the momentum distribution, and then they went on and measured the value of this contact. And this was done in calcium atoms and also in lithium-6. And since in this atomic system you can tune the scattering length, so you have this universal curve of the contact as a function of the density of this dimensional quantity, which is kf times A. Now, these dots represent three kinds of experiments. One thing that you can do in these confined atomic systems, they are trapped. So you can just release the trap and then measure the velocity of the outcoming atoms, and then you immediately know the full momentum distribution. Other thing that you can do, these are atoms that you play with this hyperfine splitting, so you can take them from one state to the other, and when you take them to some other state that is in some sense not interacting with the other fermions in the system, so you get a free particle, and from this motion you can immediately see what is the momentum of the particle. This is what they call PES, and also from the response function itself to this kind of photodissociation experiment, you can learn about the contact. This is also very clear. None of these experiments is relevant to nuclear physics. In nuclear physics, we cannot turn off the confining potential, and this experiment in which you take a particle to a state in which it is not interacting anymore with the others, this is not relevant. So even if the idea of contact is relevant to nuclear physics, none of these experimental approaches are relevant.
What are the curves on the right side?
The curve, this is actually interpolation between two asymptotic theories. At the BEC and the BCS side, you can write down things analytically, and then you just interpolate, and you get a number. You get the graph.
Right,
On the curve,
It's curves.
well, these different curves are the different temperatures. This is for 0 temperature, and this is for different temperatures. That's it. But we are, in nuclear physics, we consider only 0 temperature. So, what?
The right graph, the vertical axis is the contact.
I is the contact. For some reason, they choose to confuse everybody. So instead of doing by C, they made it I. But this I is actually C. This is the contact.
What is the, those lines are a calculation, but we don't know what it is.
What?
Yes.
This I don't recall the calculation.
Maybe it says that there's a
Right. But we don't know what the calculation is.
Okay. From a microscopical or theoretical point of view, the contact is connected with what one may call short-range factorization.
Why do you say that it has nothing to do with nuclear physics? Isn't there some regime where you get similar behavior and you can learn something about the...
I'm saying that experimental techniques are not relevant to nuclear physics.
Got it. Okay, sorry. But the phenomenon itself, of course.
I'm not. If there was no relation to the phenomenon, then the title of my talk was irrelevant. And with my many faults, I'm not that stupid. In order to get to these relations, what one assumes is that the scattering length is, okay, of course, much larger than the range of the interaction. And okay, again, density is small. Then you can replace the effect of the potential on the wave function through this boundary condition. And doing so, you immediately see that the wave function factorizes into two terms when two particles come together. One is just this famous 1 over Rij, 1 minus 1 of the scattering length, which comes for the pair interaction, and then some smooth function that describes the motion of all the other particles. And doing so, the contact is actually defined to the overlap of this residual function. And with this definition, all the nice time relations can be derived. Well, okay, formally it is just this ugly integral. Okay? So now I want to import or export these ideas into nuclear physics. So let's see what are the scales in nuclear physics. So first of all, we have to compare the range of the interaction with all the other quantities in the system. So the long-range part of the nuclear force is dominated by one pion exchange. The mass of the pion is roughly 140 MeV, which means that the range of the interaction is of the order of 1.4 Fermi. Depends if you want to look at 1 mu, 2 mu's, or whatever. Then the scattering length, we have two channels. One is associated with the deuteron, the other with, if you want, NN scattering, neutron-neutron scattering. And one is 5 Fermi, the other is 20 Fermi. So you see that this mu times A scattering is something like 4, which is not that bad. The other number that is relevant is the distance between two nucleons. To some extent, you can look at nuclei as incompressible fluid, where the radius that each nucleon occupies is something like 1.2 Fermi. So the average distance between two nucleons is twice this number, is 2.4 Fermi. So we have this result that the mu times d is 1.7.
Why is it taking the effective range to estimate this?
Well, because this will be a killer, right? Because the effective range in the, I don't remember which of the, I think this channel is 2.8. And this is just too large to make even a reasonable argument. But it's not clear that the effective range is really the relevant quantity.
It's for cold atoms.
Yeah, but not in this case.
You don't take the van der Waals length either, right?
Yeah, but depends. If you want to really fit, okay, the phase shifts in a reasonable energy range, just with, okay, with the scattering length and effective range, then you will not take the nominal effective range, but actually will take effective range which is smaller and is closer to this number. Maybe it will be 2 Fermi, but it will not be 3 Fermi.
What is the D, the 2.4 Fermis?
What?
What is D?
D is the distance between, average distance between two nucleons in a nuclei.
In a large nucleus?
Yes,
or
in a large
neutron,
nucleus.
or-
No, in a large nucleus, in a big nucleus, not in a small one. Okay. Anyway, in order to proceed, I will take two outrageous assumptions. One is that nuclear physics is dominated by scattering length, which is definitely clearly wrong. And the other is this mu d and mu scattering length. They are both, these quantities are much larger than 1. And okay, you can compare these numbers to 1, and you may say that this is not true, but don't forget this important theorem. Okay? What I shall be doing now is I will use these assumptions, knowing that their validity is questionable, but we'll see what we get, and then we reconsider them and see to what extent the results are valid.
Well, for the singlet channel, the pion is not so important. The range is probably 2 pions. So for the singlet channel, you're in pretty good shape. But for the triplet channel, and you're 3 compared to 1, then it really is 5.4 over 1.4.
Yeah, maybe.
This is not really, when you say it's a measure for short-range correlations, it's not really what nuclear physicists call short-range correlations, right? Because you're...
Let's see. Well, definitely, this is a measure for the probability of finding two nucleons together, right? This is what it gives you, the contact. In an essence.
Yes, but I mean, it doesn't tell you anything about them being closer together than the inverse pion mass.
No. It just tells you, okay, this is not defined what is close, right? What is close is not defined.
I'm just saying that, I mean, there are many nuclear physics talks where people call about short-range correlations, like that or not, but they're talking about smaller distances than you are.
So, I mean,
I'm not sure that that's true, but we'll get to that.
yeah, maybe just to comment on these two viewpoints. We did have a talk earlier in the program where short-range correlations was really understood to be within sort of 1 to 2 Fermi. And what you're trying to look at now is basically
1 to 2 Fermis.
beyond.
No, exactly 1 to 2 Fermi. Nothing more than that. That's exactly the range. Exactly. Nothing more than that, and you will see that. So let's go on with our line of thinking. So in the case of nuclear physics, we have 4 types of fermions. we have protons and neutrons spin up and spin down. Therefore, we have to consider 6 possible short-range correlations associated with all these possibilities. For each of these pairs, I can define a contact. So I have 6 types of contacts. But then I can invoke some assumption about symmetry. For example, I can assume that the spin is a good symmetry in nuclear physics. Therefore, I can reduce the number of contacts that I will need only to 4. If I go another step further and assume that also isospin is a good symmetry, which should be a good assumption for short-range correlations, because there the Coulomb force is assumed to be less important, then the number of contacts that we have to consider in nuclear physics is actually 2. One corresponds to the single channel, which are these states, proton-proton coupled to S equals 0, neutron-neutron, or NP pair in S equals 0, or a triple channel, which is just what we usually call in nuclear physics the Deuteron channel. Okay, so I have two contacts that I have to consider.
Sorry,
yes.
So what is for you, can I think of a particular nucleus that you're going to study? Just for fun?
Yes, okay, lead 208,
Lead?
calcium 40, rubidium,
Okay.
whatever. Choose your preferred nucleus and think about it, okay?
But not Deuteron.
No, not Deuteron. Well, I will almost say anything but a Deuteron and hydrogen. So now that we defined what we are looking, we have to look for these 2 contacts. The question is how to measure them or how to evaluate these contacts. To that end, I will look into this process of photoabsorption, of nuclear photoabsorption, in which a photon comes in and is being absorbed by the nucleus, and something happens. And cross-section is given by the response function, where the response function is just this transition probability square. And the transition operator is sum of electric and magnetic multipoles. They are both related to the nuclear current. Now, in order to proceed, let's again discuss scales. Yeah.
Is this measuring momentum distribution in?
I didn't say anything about measuring momentum. This is just a
current. I didn't know that.
no. This is a current.
What is current?
A current is the electric current, the same that you teach in high school. Just the motion.
Scattering the electron off the nucleus by exchanging the
No,
photon.
no. This is just photons come in, it's being captured by charged particles, and something happens. This is the process. Okay?
So
this
it's
is-
photon nucleus scattering.
No, not scattering, photoabsorption.
And what is the final state?
This is some nuclear
All-
state.
You're considering all possible final states.
Yes, of course. You have to consider all possible things that can happen there.
Okay, I'm not understanding this as a measurement, I guess.
What?
Is this a measurement or a misunderstanding?
No, this is a measurement. You make an. Okay, I will go to. You have an incoming photon, okay?
Yes.
You produce the photons by some miracle mean, and then you have the nucleus, and then you measure what comes out. Okay, this is experiment. It has been done for decades now.
So
What is the
so
difficulty?
Is the nucleus breaking up into different pieces? I mean, you
Yeah,
say
of course. Or it goes to some excited state, depends on the energy. Yeah.
Because as an atomic physicist, I would say he absorbs this photon and then emits this photon again in some random direction. You detect this photon.
Okay, no. In this case, it's usually what happens if you deliver enough energy, you break the nucleus. This is the process. And we are discussing high energy photons, so the process is breaking up the nucleus, definitely.
So
You can.
don't measure the elastic photons coming
No. I measure outgoing protons or neutrons. Yeah.
Water and alpha.
Yeah. what you discuss is really high order, like Compton scattering, well, this is what you discuss. This is not the dominant event, okay? As I was expecting, this is a kind of a question that I was not expecting, but this is the really language mismatch or cultural mismatch. Okay, point understood now. So, some scales. Nuclear physics, we use MeV and Fermis, and if we have a photon of 100 MeV, then the inverse wave number of the photon is 28 Fermi. Okay, this is to be compared. Then it is, if it is 100, then it will be 2 Fermi. Okay, and this is to compare, for example, to the size of lead, which is about 12 Fermi. Okay, so if I have a photon of 10 MeV, then it will be roughly the size, wave number will be the size of the nucleus. When I go to 100, it will be roughly the size of twice the nucleon or the inter-nucleon distance. Okay, so these are the relevant scales. Then what we can do in principle is see what happens as we do this photoabsorption experiment as a function of photon energy. So
can I ask again about the lead? Lead is your favorite nucleus, I guess?
No.
Some people's favorite.
No. Just I have this picture.
So, but if it's not your favorite, then I can imagine you're going to show us data as function of the size of the nucleus.
Yes. Yes.
You're going to show us finite.
Yes. Of course. But this is right to the end. So what happens? What? I didn't get it.
You said you weren't going to talk about the deuteron, but it's on the slide.
No teasing allowed.
No, teasing are more than welcome. It's just checking my stamina. So here you see what would be the response of a nucleus when you change the energy of the photon. So when the photon energy is few tens of MeV, then the wavelength sees really all of the nucleus. So you have some kind of collective behavior. All the protons react simultaneously to the photon field. So then we get what we call giant resonances, which is collective motion of the whole system. Then when you go to energies of the order of 200 MeV, you see this peak. This peak, okay, there are some experimental data that come from 3 different nuclei, and you also see the proton on top of it. So this is actually associated with one particle absorbing the photon and going usually from a nucleon state to a delta state. This is what you see here. In between, it is the range that is interesting for us. This is what is known in nuclear physics as the Quasi-Deuteron range. Because here, there is a theory that comes from the 50s that the cross-section is dominated by photoabsorption by 2 particles. And I will show you why this is relevant to our story. Now to the neutron cross-section. What you see here as a function of energy is the multiple decomposition of the photoabsorption cross-section. And you see that the E1 and M1 are the dominant contributions at essentially for any energy range. But you can also see that this isobaric resonance is associated with the M1 transition and not with the E1. This peak, this resonance is associated with M1 transition and not with the electric E1. That means that if we consider only the E1 transition, we will see the tail of this quasi-deuteron and will not be affected by this isobaric behavior of the cross-section. Okay?
Once again, it's the only region where this description might be valid is in the dip between the 2 peaks.
Yes. in this tip. We're discussing this tip, but you have to consider that if you are analyzing your data in a different way, not looking at the exclusive, inclusive cross-section, but only at the E1, which you can in principle do. Okay, if you integrate, you look at the distribution of the outgoing particle with respect to the polarization vector of the photon, then in the E1 you will probably not see this peak. Okay, and then this dip will go on, because this is what you will see in the E1. Okay?
Do you have a graph of the cross-section for E1?
No, I don't have.
Is it measured?
I don't know.
So E1 is not this what you call GR.
No. GR is just the behavior of the, actually the GR in some cases is dominated by the E1. But just to tell you that the E1 is the quantity that we are going to look at, okay? Because it is cleaner in the sense that at high energy you don't have this isobaric transition, okay? So
do you have Fermi motion, the Fermi broadening that here?
everything you got there. This is experimental results, right? So we go to the E1. The E1, at least at low energy, it's an extremely simple operator. It's just the sum of the particles, charge, time, their position. Okay? In the nuclear physics language, we write it like that, but okay, that's not important. Qi is 1 for a proton and 0 for a neutron. That's it. So what I would like to do now is just consider this transition matrix element and see what comes out of it. So now let me take you back to, okay, the year 51. At this point, which was early time for nuclear physics, Levinger has proposed a new mechanism for photoabsorption. And he pointed out that at high energy, the nuclear photo effect must go through a two-particle process, because the photon carries no momentum, but essentially only energy. This energy is absorbed by a proton, and if a proton takes this energy and runs away, then there is a problem of momentum conservation. So in order to provide for momentum conservation, some other particles must be emitted in the opposite direction. And since he was also considering that this process must be dominated by the E1, which is the dipole, a proton-proton pair have no dipole, so this partner must be a neutron. Consequently, he assumed that there is a proton and neutron that are flying out back to back, and therefore he formulated what is known now in nuclear physics as the Quasi-Deuteron model. He said neutron-proton are like the deuteron. At short range, the wave function should be universal. You don't really care about the other nucleons moving around. And as a result, he derived this formula for the photoabsorption cross-section of any nucleus that's saying that the cross-section of nucleus with A nucleons would be some parameter that he have calculated times the number of neutrons, number of protons divided by the number of nucleons times the Deuteron photoabsorption cross-section. This is the Quasi-Deuteron model of Levinger, and L is the Levinger Constant. And he estimated that this L should be something like 7 or 8.
It's also possible singlet Deuteron, singlet state of Levinger.
Yes.
Is it somehow included?
No, ignore that. You say, okay, this should be dominated by the Deuteron, and assume anyway that this should be very similar.
Triplet channel dominate.
You will immediately see that this is justified. Under this assumption, that's okay. And okay, you will not be surprised to realize that this L of Levinger is actually a close relative of the contact. So, and this is what I will try to convince you in the next few slides, that actually this Levinger formula can be re-derived in terms of the contact and the assumptions that Sheena produced in the atomic physics. So I apologize now for a few heavy slides. So the wave function nuclear wave function takes the following form when the two nucleons come together. Now we discuss.
Tn to 0 is not really correct, right? Because you
Well, what I failed to mention is that now I solve the nucleus in the zero range model. Okay, so we have to refine that later. But at the moment, I work in a zero range approximation. Therefore, this is the correct form. The only difference between atomic physics and nuclear physics is in this case I have to consider two channels, right? One in which the nucleons are in spin 0 state, and other in which the nucleons in a spin 1 state. So this is encapsulated in these functions.
This formula is really for scattering and zero energy,
Yes.
and the nucleons are balanced. So of course that's a large distance effect. But what I'm really asking is that 1 over AP, is that really the free scattering line? Is it?
Well, actually the 1 over AP is not the essential part of this business. What is really essential in Sheena's derivation was this 1 over R. And for me, what is really essential is this factorization, okay? And at the end, it's not really important what is this function.
What is the sum over?
The sum, okay, I was saying that we have to consider when the two nucleons, the neutron-proton pair, come together, they can either be in a singlet spin state or in a triplet spin state.
So it's not sum over protons.
No. P is the sum of the possible pair states, okay? And
P is not a proton, but is N a neutron?
no, small p is a proton and small n is a neutron. Capital P is a pair state, okay? This is capital P.
And where else in that equation is there another capital P? I can't.
Okay, this is capital, this is capital, this is capital, this is small, okay?
On the high, that's a capital.
Where?
Next line.
In high?
Yes.
Yes, this is capital. Okay? Sorry.
I came in late, so I may have missed you said this, but the physics of this is involves the tensor force very strongly, and that's been shown in inelastic electron scattering
Yes.
experiments. So this treating it all as S-wave is a nice model, but it isn't the real physics.
I completely agree,
Okay.
but still,
Okay.
it's nice to play, right?
Yeah, right.
We'll have to refine it later, but maybe not in this talk. Anyway, this is the major difference to what is done in atomic physics, because you have to take these possible spin channels, and you have to consider different angular momentum for the spectators' nucleons. But okay, otherwise, this is essentially the same. So this is the ground state. Now we have to consider the final state. So following Levinger assumption, for the final state, we have a pair of neutron-protons that absorbed the energy of the photon, and they are moving out very fast. They're moving out that fast that they don't interact anymore with the residual system. So their function, the final wave function would be just this pair going out as a free wave, and all the other nucleons remain in the same position. And
That's a major assumption when you have a heavy nucleus like lead. I mean, if the photon happens to be absorbed in the middle of lead, the proton and neutron have to get out.
yes,
And they'll certainly interact.
okay, there are two kinds of answers to this remark. One is that if you go to high enough energy, then this approximation becomes more and more becomes better. Then you can also consider the reaction as what people usually do when we discuss nuclear reaction in these systems as a two-step reaction. First is the photoabsorption, and then there is this a consequence reaction. And this is the way people analyze anyway the reactions. Seems to be a reasonable assumption as a two-step process. So this is the first step of absorbing the nucleons, and then something else happens. Okay?
You can inclusive cross sections, right? So you don't.
Yes. So I don't
if
care.
that proton
Exactly.
reacts
Exactly. I don't
way
care.
out.
Yeah. So this is just okay. The initial condition for subsequent events. Okay. Now here I have to take into account anti-symmetrization. I have to account all possible protons and all possible neutrons, and some normalization because the wave function needs to be normalized. And with some algebra, you can see that we have to consider a specific pair in a specific spin state, and this normalization is directly associated with the contact in this state. Okay? So now that I have the initial and final states, I can go to the transition matrix element. And again, for the dipole, this will take this form. Now, since we are considering really a high momentum, so this will be short distance, so also for the ground state, I will replace the wave function by the asymptotic form. And this amount to this kind of integral. Now the one thing that I would like to do, I have here on the outgoing, this residual system that corresponds to a pair in a specific state, but on the right end, I have to consider all possible couplings, either spin triplet or spin singlet. Fortunately, this dipole operator has no spin dependence, so I have this delta function, and after some algebra, you get that the transition matrix element is proportional to the square of the contact times these kind of matrix elements, that you will not be surprised that this is just what you get under these assumptions for the Deuteron. Because you see, we have just the distance between the proton and the neutron that come into play. Of course, here I have the two possible scattering lengths. One is for the neutron, the other is for the singlet state. But anyway, in this integral, this is the important part. This is the not important part. So this is roughly the same. And now, with some algebra again, we get to these relations that the matrix element for the dipole operator between the A body states is just something that is proportional to the neutron matrix element. Okay? And this is essentially Levinger's result. Okay? Re-derived using the language of the contact. So now I get this cross section for the photoabsorption of general nucleus, and we see that this is proportional to the scattering length in the triplet state times the sum of these two contacts, the singlet and the triplet, and times the Newton photoabsorption cross section. And now I can compare it to Levinger's formula, and immediately I get this relation that the Levinger constant is nothing but the two nuclear contacts times some known parameters. So,
Can you
yeah.
go back to the previous slide?
Yeah.
I'm sort of wondering about this statement in the
This
red-
one?
Yeah.
Okay.
Where, earlier you sort of answered to Jerry's question that it doesn't really matter what the AP is.
Yes.
But, I mean, if these quantities differ by a factor of 2, your contact is going to be off, right?
No, well, this is, okay, either 1/5 or 1/20, right? And the integral is, okay, dominated by this one, okay? it may imply an error of 20%, okay? But okay, this is easily bearable at this moment. I'm not worried about 20%. Order of magnitude to be scary, but 20% is completely acceptable at this level of discussion.
And that formula for L,
What?
I can't read from back here, but
Oh, there is a chair here.
there's an A with a subscript. What is the subscript on the A over 8 pi? T.
T is for the triplet. This is for the scattering length in a triplet.
But your C's are for S and for T?
Yes. This comes from the normalization of the Newton wave function, this AT. Okay? This is just for the normalization, nothing more. So now I can also define the average proton-neutron contact, which will be just the average of these two quantities. And now we have this nice relation.
There are 3 for the triplet and 1 for the singlet. Right?
No, there was 1 and 1.
3
No, of course,
states.
there are 2 contacts. But the singlet, of course, corresponds either to proton-proton, neutron-proton, or a neutron-neutron. But in this process, because I'm dominated by the dipole, I look only at the neutron-proton. Okay? So essentially, this is my final results, which relate the Levinger constant to the neutron-proton contact. And since L was measured experimentally or evaluated experimentally, now I can deduce what is the value of the nuclear contact, at least in this channel, in this average sense.
So why is A over NG so constant across different nucleus?
I didn't say that. I didn't say that it is constant, but for each, it might be a constant, it might be not, but
C depends on NZ and L.
But principally, if you think about a symmetric nucleus, okay, well, n equal to z equal a equal to 2 divided by 2, so this factor is roughly a constant, okay?
But you know, there were severe, I mean, in the 70s, people did a lot of work on the corrections to Levinger's
Yes.
idea to do a meson, to get to that. I don't see meson exchange corrections.
Okay, okay, let me...
And they're not in the scattering.
Like more than the
50%,
20%?
70%. I mean, my memory, it's from the 70s. So
Yeah. Okay, let me, okay. Okay, so far we have used really very, very simple assumptions, and we got very nice result. Now, as you all said, okay, these assumptions are some sense outrageous in nuclear physics. So let's see what is essential and what is not. What is essential is this factorization. If you can write this function, the wave function when two nucleons come together as some universal function time a residual function, and of course they have to be coupled in some way, then this result will hold. Maybe if this is not an S wave but a D wave, one have to be a bit more clever about the algebra, but I believe that this result will hold. I was considering so far only this S wave states.
What does RPN going to 0 mean? So what values of RPN is really valid?
Well, they should be, if you want, you should be above the Fermi momentum, okay? So if the Fermi momentum is 1.2, so you should be in this range, okay?
Shouldn't RPN also be larger than the effective range?
No, not necessarily, because I don't care anymore. You see, this function could take now into account anything you want, as long as it is universal. The only assumption that you need is that this function is universal. Then, of course, if it is not 1 over r, it is not dominated by the scattering, you will not get this C over K to the fourth. This will be lost.
Why should it be universal? I mean,
Okay, all these questions for one slide, okay? But I'm saying if this is true, then everything else follows, okay? I haven't used any particular property of the wave function of this 1 over r minus 1 over a. The only thing that I use is that this is really universal when you go, you come together, okay? So this is really in essence, the assumption that is needed, not this assumption. This is one thing. Then about the currents. For the currents, again, what was needed is just the orthogonality of these different channels. Now, in general, then you don't care whether you have meson exchange, you don't have meson exchange. That's not important, as long as you have this orthogonality. And anyway, if you're considering a spherical nucleus, then even that is not important anymore. That the orthogonality will follow from the orthogonality of these states. So therefore, this question about what is really the details of the nuclear currents are completely not important, or one can ignore them. Then another comment is that if instead of looking at the total photoabsorption cross-section, we will be looking at spin correlated pairs, then the cross-section will be proportional only to the triplet contact. And then I'm able to, in principle, to distinguish between the singlet and the triplet contact. So far, we didn't find experiments that actually look at that, at this quantity. But in principle, this could have been done, and then we were able to distinguish between the singlet and the triplet contacts. Now,
Can I ask this just about detection, because there's always at a given moment in your experiment only one photon in the nucleus.
no, but in principle,
Shine into it.
What is the question?
I mean, how this is a very useful formula for me. Gamma is plus AX, and there's only one gamma. There are no two gammas.
Right.
yes.
So that's
Well, in principle, the modern way people do these kind of experiments is that not only that there is a single photon, but you know its name.
What's his name? Joe, Harry?
Exactly. What is done is the following. There was the way to produce photons is through Bremsstrahlung. So you get a whole spectrum, so you don't really know the energy of the photon. So people struggled with this issue, and at the end, what is done is the following. Okay, it will be this side. It's nice that the theoretician is explaining the experimental apparatus. So what you have is an electron beam, okay, that comes with the energy that you wanted. Then they produce, they hit a thin target, and they produce your gammas, okay? And then you put here some magnetic field, okay? And the electrons continue, and then you measure the energy of the outgoing electron. So if the intensity is so low that you know to associate your gamma with this electron, so you know the energy of the electron. Therefore, I'm saying not only you know your photon, you know its name, because you make the correlation between the electron and the photon. So
your timing is good enough to know that.
yeah,
it's the right
exactly. So this is really at very low intensity that you do these experiments. Okay? So, answer to your question about this factorization. So, people looked at this issue for, many decades now in nuclear physics. And using electron scattering, people deduce, this work of Joe Fideliati and Simola from '96, the momentum distribution of the nuclei, of different nuclei. And you can see that at the tail, these are, models, but, okay, they take into account also the correlations, you have the same behavior. So it seems that this factorization is justified. Of course, it will not be the same factorization as we have in atomic physics, but there is this kind of factorization.
What is the power law of the tail?
We started to look at that, we don't know yet.
So this can't all be experimental data because
This one, yes, I was wondering, in the subtitle for the for this figure, it's written experimental data, and there's another article from 2012 that also takes this picture and also said experimental data, and I was,
Extrapolating.
yeah, this is my thought, yes, that this is just extrapolation, but yeah.
But how do I see from this picture that your phi p is universal? This is not clear to me.
Well,
Phi even?
I mean, this the
Separation.
yeah. So
no,
this
you don't see it directly, of course, because this is phi p square, but you see that the high momentum behavior of all these nuclei is very similar. And actually, if you divide them one by one, all the tails, that they flatten out.
What's the difference between this guy and this guy?
With okay, this is a naive naive model, naive shell
it
model.
must be a shell model.
Yeah, this is a shell model. This is just a shell model.
And the other stuff is
And
the
that-
tail.
And in the nuclear matter, this is just a simple Fermi liquid, Fermi gas.
Experimental on, what does that say, helium-3?
Yes, there are some strange results here. I don't remember what is the difference between this set and this set.
And there isn't any data at all for oxygen, calcium, and lead?
Well, this is what they had at 96. I don't know what the situation right now.
There was certainly data, of course, there's no, I should know this better, I've read the paper many times.
Well, I think that it's not only that you had
NFA is not measured experimentally.
yeah, this is actually extracted from the experiment. This is not
Extracted
directly.
from E-prime
Yeah,
experiments
exactly.
In a fairly complicated way.
Yeah, this is not a direct measurement, of course. You have to assume certain things about the cross-section in order to deduce this quantity. Assumptions that are very similar in nature to what I have just presented here.
Yeah, I mean, the model is basically built that the deuteron is just the short distance
The-
part
the-
of the wave function is essentially the deuteron for all nuclei except for a number. The heavy nuclei have more deuterons.
Something like that. Anyway, there was a workshop here, something like a year ago, that I think you were one of the organizers that discussed all these issues that are very strongly related to all these discussions. So, and I think that these two languages can be matched together. So now let's go back. Hi.
Good way.
I don't need more than 5 minutes. So the way people extracted this Levinger constant is just looking at photoabsorption cross-section, taking, this is in red, the dots are the data for the carbon, the curve is just the Deuteron photoabsorption cross-section. You multiply it until you get satisfactory description of the cross-section when you are out of the giant dipole resonance range, and this is the way you fix this L. So this was done over the years, and Levinger essentially initially said that L should be 6.4. Then other people like Tavares, the Terranova in the 80s and 90s reevaluated this result, and this is what you get. We have reevaluated their data, just took these points and tried to see what we get. Essentially, we get this kind of constant, and it's very narrow, and I don't see any A dependence here. So for me, this is a constant. And then you can look at symmetric nuclei and see what you get, and we get this value for the nuclear contact, which is roughly 2.7, and our KF a triplet is something like 0.15. Yes.
So this formula you showed with the A dependence, did that analyze the same data that you analyzed and got a constant value, or
This you mean this this formula?
Formula is from the data.
Is this line? Yes. And this is the same data. Yes.
It's the same data.
The same data. Yes. I think that if you impose that it must be 2 at 2, then this is a strong constraint. I didn't impose this constraint.
Why are the error bars at an angle?
This is because they used a neutral target, so it means that A is not well defined.
So why don't you use data on the Deuteron?
What?
Why are there no data on the Deuteron?
Well, the Deuteron is by definition 2. Okay.
But I mean, you can evaluate the contact in any.
Yeah, that's
in
true.
any state,
That's
so
true.
you can
But
evaluate the two-body system.
yeah, of course. But
Why not do two-body system?
yeah, I think that in our case it will be, yeah, you can do that, yes. But it will be some kind of a trivial result.
I mean, there should be lots of data on.
Some with
Yeah.
3 nuclei, 4 nuclei.
Yeah, but okay, in our case, in the way I extract it, we will not get a meaningful contact from the Deuteron, by definition. So let me,
There's no helium data, for example?
what?
Why is the helium not on there?
The helium, I think this should be the helium, right? Or, okay, this is not the helium.
That is 6.
I don't know why the helium is not there, but anyway, at 92, no, there should have been results for helium. I don't know why they didn't include that. I don't know. They make their peak of results, and we just took what they have done. Of course, one can add more experimental results and do the analysis. At this point, we just took what they have done. So just one last comment. So this is experimental results on atomic systems as a function of KFA, and blue dots are calcium, and brown squares, this is lithium experiments. That's K is potassium, yes, sorry, yeah, Ca is calcium, right? I know the Hebrew name. I know the Hebrew name. So the question is, how does our results for nuclei fit into this picture? So this is the answer. Surprisingly enough, it seems to be consistent with this atomic data. Of course, under all our outrageous assumptions. Now, the reason I have this large error bar in the x direction is because I don't know which scattering net to take. So I can take either for the triplet or the singlet, and all this range is just from all the possible nuclei that we got. So I think that now I'm almost in time. Okay, this is what we have done, but you know all this by now. So thank you.
Yeah, thank you very much. Eric?
You motivated this by considering the limit where both of the nucleon scattering lengths are large. And in that case...
No, this is not the motivation. This is not the motivation. The motivation is that, essentially is that there is a universal behavior when two nucleons come together. This is really the motivation.
Okay, but an example of, I mean, early in the talk you had if you like, a model of
but
scattering length.
this is just to make derivation simple.
In that case, there will also be a three-body contact that plays an important role in that model with two large scattering lengths.
Yes and no. Of course, there is also a 3-body and 4-body contact and 5-body and whatever.
There's a three-body contact.
Well, there's also 4-body contacts, right?
No.
Right. 4 nucleons can come together to the same point, right? So there could be also a 4-body contact.
No.
Why not?
For the same reason that there isn't a 4-body contact for bosons with large scattering length.
Is that
Why?
every multi-vector?
Yes. Yes. If you have two large scattering lengths, there's an FMO effect in the two-body problem. In the same, in that case, the three-body contact will.
Well, we look at the different definitions. For me, the definition of a contact is just a probability of finding few particles close together.
So it would mean your four-body contact would be zero according to you.
Well, it would be higher order,
Because
right?
you're saying that basically you don't need something to renormalize the four-body problem.
There won't be anything like a four-body contact that has universal properties
Yeah.
analogous to the two-body and three-body.
Well, I was not saying anything about universality yet. Now, the question of universality is associated with the structure of the wave function of short distance, whether this is universal or not. What we try to do here is to evaluate the two-body contact. And the three-body contact, its effect on this process should be very, very small, because it's proportional to the probability of finding a triplet that close, and this is much reduced.
No, it's not, because of the FMO effect.
Not here.
Not here.
If you have the case of two large scattering lengths, it is inevitable.
So I think
I'm not sure. I don't think so. I don't think that you are right.
this is definitely something I think that calls
Well,
for
the
more.
situation only can you correspond to Triton, I think.
Yes.
Triton has a finite energy, so we know that there is no huge distribution here.
Yeah.
Constant type.
Another puzzling point is this is a four-component Fermi system.
Yes.
So it's why the result is in line with the contact for the two-component Fermi gas.
What? I didn't.
I mean, so the curve you showed for the
This
contact,
one?
this is for the two-component.
Yes.
Fermi gas.
So
But the nucleus is a four-component.
yes.
So,
So as I was saying, because of symmetry, spin and isospin, you have to consider only two contacts. Now, and I'm considering only a proton-neutron pair, and they can be either in a singlet state or a triplet state. And what I plot is the average of these two contacts. It might be that one is here and the other is here. I don't know. But the average seems to be here.
So I think at this point we'll thank Nir again. And we have a second talk at 20, so in 5 minutes by Xilin Tang. And then also we'll have more discussion on Nir's presentation in the afternoon at 3:30. Thank you very much. So I think